Hey there, calculus fans. This is going to be a proof of the product rule, but the target audience is my business math course. They're not required to know the proof of the product rule, but I always feel bad jumping past something. So this is going to be a supplemental video to my course. It's not required for you to know this in my business math course, but we've been talking about the definition of the derivative, f of x plus h minus f of x over h. And students have been confused by that. And this video probably won't help that. But you have some function and you have 2 points. And the goal is to define slope at a given point on a curve, but you can't really do that because you need 2 points to do the slope. And so what we did is we picked another point nearby, and that's what this was. And we called x plus h because we're being clever. We're trying to write it in a way that it's easy to just look at what's changing. Some people write the definition as f of b minus f of a over b minus a. That's also correct. And then we let a get closer to b or b closer to a, and then we talk about the derivative. But the standard definition is this. In a calculus class, we add this little symbol out in front, the limit as h goes to 0, but we don't do that in our business math class. Oops, I just did. So the idea is we find the slope between 2 points on the curve, and then we ask what happens if the 2 points get closer together. I know that sounds like a lot, but calculus is built off of these limiting processes, and all that would be crazy except for the fact that we can actually prove what the limiting process gives, and it has a bunch of nice short rules, which we've learned. We've learned things like the derivative of x squared is 2x, and the derivative of x to the fourth is 4x to the third. And we've played that game already. We actually talked about why that was true. I even said a little bit about Pascal's triangle, which I probably shouldn't have done, explaining why it's true. So the question becomes, what happens if we have the product of two things? And I've made up an example here. I know it looks bad in the setup, but it's this example. I have this, and I have this. These examples are big, just because there's more stuff going on. But it's the product of two functions, the first function and the second function. I've drawn you a picture of it. It's this green thing. Notice it has a couple bumps, a high point and a low point. So if we wanted to find those, we might want to be able to find the derivative. Now, there's a couple ways you can do that. One is you could expand, which probably is the best way, given the size of this. Sometimes things are so big that you just want to use the product rule. And at this point, we don't have other types of functions, so we don't need it that much, but we will later. But this, you can expand x to the fifth, so I'm doing this times this, and then this times that. So we'll do, it's going to be a 10x squared. And I'm just going to do this for comparison, because in a second we're going to do the product rule, and then I'll finish with the proof, because I need us to understand a little bit of ideas first. So there's going to be a 2x to the third. That's the mouth. And then we're going to be, and if you're not one of my students and you go, did he just say mouth? Yes. This is the nose. And all of this is a monkey face. Doesn't it look like a monkey face? My students this quarter did not even snicker or laugh in any way. They put me in my place. Okay, so the derivative is 5x to the fourth plus 20x plus 6x squared. And I admit it wasn't funny. Plus 20x to the third. Okay, that's the derivative. The product rule gives us another way. And if this was the only example, we wouldn't need the product rule, but we do need it. The product rule says, like I said, as you'll see this more when we start to incorporate other functions besides polynomials, but even for polynomials, we need it. So this is the first function, this is the second function, and the product rule says the derivative always is the first times the derivative of the second plus the derivative of the first times the second. And when I write that, I mean that f and s are functions of x. So I tell students you can just fill in. Write down the first function. I personally like to write down everything and leave the derivatives for later. So let me space this out so you can see where I'm at. And this is times the derivative of the second. I'm going to leave that for later. And then I'm going to do the derivative of the first. And really the order doesn't matter. You just need to do both derivatives times the second. And I tell my students, that's a lot of hard work what we just did. We had to write down 2 things. So at this point, if you need to take a break and go have lunch, that's fine. Because then you can come back and you have 2 smaller jobs to do. You need the derivative of the second thing, and that's much tamer. 3x squared plus 2. And the derivative of the first thing, which is 2x plus 5. And what I'm claiming is that this is the same as what we would have gotten by expanding. Now, proving that takes a little bit of work. You could expand it out. Maybe for the video, I shouldn't do that, even though I really want to. So for those watching, expand it out and see if they're the same. Hopefully they're not, because that would be a lot more exciting. Okay, okay, so I'm going to get rid of that, and I want to explain why these are the same, what the standard proof looks like. Okay, so here we go. Let's get rid of that. Let's make that vanish. And what we're trying to do is to describe this thing we call the derivative, and this is the derivative. The derivative is the slopes of these tangents. And I'll show them side by side in a second. And unfortunately, it doesn't work to just take the derivative of each separately. So someone said, all right, that's fine. I have 2 functions. Let's call it f of x times g of x. And maybe all the f's are bothering people. So let's change the name of this to something. Let's call it a of x. This is Andy's function. Oh, L of x, the loveless function. Okay, so we're going to use this here. So I need to plug in an x plus h. So I'm going to write down the definition. I have a product of 2 functions, and I am going to write, and I had to do this in grad school. I think this was on one of our tests. Part of what you do as you go higher is prove why things work all over h. That's what we're trying to analyze, and we're trying to simplify. We're trying to say something about that. It is not obvious how to simplify that at all. But somebody came up with a clever observation. I suspect whoever first saw this just did examples and noticed that this pattern by doing lots of examples and then tried to prove it. That's my suspicion. I don't know that for sure. But my goal, once I kind of have an idea, this is the proof I have in my notes, was to add something in the middle. And you can't just randomly add something in the middle, but we're going to. So the proof goes like this. It says, I'm going to add, and there's a bunch of ways you can do this, and I'm going to see if I can match my notes. We're going to add f of x plus h times g of x. So what we're saying is we're going to go to the x value, wherever that is, plug it into g and get that y value, and then we're going to x plus h and plug it into f and get that y value. The goal is actually to try to kind of mix things together, but you can't just randomly throw something in. But you can if you subtract the exact same thing. This is the clever idea, to add and subtract the exact same thing. And what's happening is h is getting smaller and smaller. We can rearrange things a little bit. So what we did is we basically added 0 in a clever way. That was 0. But now we're going to rearrange it. And the observation is that this and this are the same. So we can take those first 2 terms and factor it out. Again, this is not this is not for my students. And I realize I made a small little issue, which is I should have had this be a minus and this be a plus, which I realized immediately when I wrote this next step. Okay, so when I take those 2 things out, what do I get? I get g of x plus h minus g of x. You're like, he's just pushing symbols around. I'm trying to relate it back to the derivative for g and f, and I'm starting to see some things appear. Now, for this one over here, what do I see they have in common? They both have a g of x. So let's yank that out. G of x. And then we're going to have an f of x plus h minus f of x. Okay, are we getting anywhere? Well, all of this needs to be divided by h. Since it's a fraction, you can divide this by h and this by h. If I was in class, I would say, do you believe that? Well, how would you then add the fractions back together? Well, they have a common denominator, so that's also the same. The last step is just an understanding of how fractions work. which is this times g of x plus h minus f of x. And then I would have you, if I was in class, say, what is that thing? And then I'd write g of x, and I'd have dot f of x plus h minus f of x over h. And I would ask you, what is this thing? The truth is, as h goes to 0, this gets closer and closer to what we've been calling g prime. As h goes to 0, this gets closer and closer to f prime. We're left with one more thing, which is what happens when h goes to 0 there. You're just left with f of x. So it's a satisfying little proof. It's just we don't do it in a business math class because that's a whole different animal explaining something like that. But I think some of my students will appreciate that. These things don't come out of thin air. We have a definition. We see what we can say. And what's cool about that proof is it applies to any situation where there's a product. And with it, we can then try to figure out where the bumps are. So what I've done here, make this a little smaller. You can see a few cool things. For example, when we're at the peak, right there, the slope is 0. So if I could find the derivative and set the derivative equal to 0, this is the derivative down here. The place where that was 0, you're at the peak. Then if you move, the derivative is negative, and this is what we're going to be practicing as we go through the next sections. Here we have the derivative is 0 for just a moment. And then it's positive. And this is the part in calculus you'll practice. Just making this a little larger, which is being able to look at this and realize what's going on. That slope is changing from positive to 0 to negative. That means the actual graph has a peak, uphill, 0, downhill. And then we have negative slope, 0, positive slope, which means downhill, 0, uphill. Those are the fundamental ideas in using calculus. But we wouldn't have been able to analyze a function like this that easily without knowing this product rule. Okay, hope you found that